kind of at the heart of all that, and I guess at the heart of much of your work over many years. So, thank you.
Thanks very much.
I have a remote plug, so.
Oh, okay, good. Sorry to be late. It's a combination of oversleeping and the horrible traffic out there. So, started the tour in Oxford and had a very warm reunion with Cliff Jones. He's working very hard to celebrate Strachey's 100th birthday. Strachey was born in 1916 to a crazy family. And so they're going to celebrate that in November in Oxford. I met Strachey in the summer of 1969. I was on a IFIP working group, language definition languages. We never knew what the title exactly meant, but there were a number of people taking part in that. But at that meeting, come in if you're coming in. There's lots of seats here. What I found in that meeting was that I thought Strachey had had quite a lot of experience starting his own company, but he had worked earlier at Cambridge on the never-finished CPL programming language. But anyway, his ideas of what a programming language should be made the most sense to me. So I went then, arranged to visit him in the fall of '69, and that's when I started on to develop the models for the Lambda Calculus. Quite by accident, I never intended it to, but they came out of the things I started there. Then in '72, quite out of the blue, the call came from Oxford they had just established the first chair in mathematical logic in Oxford. In the meantime, Strachey, with his success with the programming research group, had a personal chair in computing. Then after his death, that was made a permanent chair, and Tony Hoare was the next holder after Strachey. But Oxbridge is governed by the academics. So when I got there, I was on the LitHum philosophy, LitHum faculty committee. I was on maths. Computing was starting up. There wasn't yet a computing program. Strachey was very much absorbed in getting the department together. We never had a chance to work together again because professors have so much administration there, and then very sadly he died. So many good things, of course, came out of the development of the PRG, and the computer science department. I have many colleagues there, but I had really hoped for a long-term collaboration with Strachey that didn't take place. Let's see, on the topic today, how many of you were not at Imperial? Okay, a lot of you. So I have to repeat a little bit of the talk from Imperial, and the part of the talk concerns Lambda Calculus. What I'm going to do is to graft, in a certain sense, type theory on top of Lambda Calculus. In the talk I gave at Imperial, and Abbas has the slides from that he can share with you, to do random variables, it was really much more convenient to have my model for the Lambda Calculus. But in the talk today, we could have basically any model for the Lambda Calculus. The model I'm going to describe is very rich, so it has lots of extra structure that could be uncovered on it. But if you just want to have a formal setup for giving semantics for the type theory, and I'm thinking of Martin Lerf's extensional type theory, you could take any model for the lambda calculus. You could even take what are called partial combinatory algebras, and the first one that's very popular is the one defined by Steve Claney. He said, take the ETH Turing machine and ask what function the ETH Turing machine computes, and say apply it to an argument. This is a partial operation. That's why it's called partial combinatory algebras, because it just has a partial application operation. The model I'm about to describe that I like to use here for today is a total combinatory algebra. Of course, you can get all kinds of partial combinatory algebras if you take Curry's combinators, and you take combinators in normal form. Then when you apply one combinator to another, sometimes that has a normal form. Of course, it can have not a normal form if I write in terms of lambda calculus and take a crazy thing like lambda x of x, if I call that d for diagonal, so to speak. Then if you try to simplify d of d, you waste your time doing it over and over and over again forever. It does not have a normal form. So if we take the combinators with normal form as being the definite ones, then application sometimes has a normal form, sometimes doesn't have a normal form, and so it's a partial operation on normal forms. Normal forms, if you're careful, can be defined so they're unique. So you reduce that to normal form when it's well defined. Those are examples of partial combinatory algebras. Okay, everybody with me on that? So I'm going to now define my version of the total combinatory algebra. I'll skip over that one. With lambda calculus, so I'm going to do it in terms of lambda calculus. So the axioms for lambda calculus are, since it's a bound variable, you can always rewrite bound variables. But the key thing is if you take a lambda abstraction and apply it to an argument, you then find out what the answer is just by substituting the argument, being a little bit careful about free and bound variables, into whatever expression it is that the lambda abstraction is supposed to define. And I'm not going to assume eta. Many people like eta there, but I say it's an unnecessary assumption for applications of lambda calculus. Everybody moderately comfortable with lambda calculus? Do you know that it's equivalent to combinators? Curry's combinators are k lambda x lambda y x and s lambda z lambda y lambda x. S is a kind of point-wise application, and k is the constant function that gives a constant value. And Church introduced lambda calculus, and in the meantime, in his work in Germany, Curry discovered combinators, And then it was realized that really combinatory logic, I don't mean logic, but the equational part, and Church's lambda calculus are equivalent. So, in other words, lambda expressions can be generated under application from just two things. If you want to be really crazy, you can generate it from one thing, but it's irrelevant what those things are. Now, the model I'm going to describe here models lambda calculus or combinators in terms of sets of integers as infinite data objects. We begin with finite integers as finite data objects, and then we take a set of integers as an infinite data objects, and you think of that infinite set as the limit of its finite subsets. Now, to structure the integers there, I use a very simple amount of Gödel numbering. First, they're ordered pairs of integers, and there are hundreds of different good computable, even polynomial functions. This is not polynomial for numbering ordered pairs, but every positive integer is uniquely factorizable that way. So every positive integer represents a pair of integers, and either one of n or m could be 0, but the pair itself is non-zero there. Once you have pairs, it's a very cheap thing to do to interpret sequences as pairs of pairs of pairs of pairs of pairs, a bit like in the Lisp language there. So we can let 0 be the Gödel number of the empty sequence, and then longer sequences, you just do a const with pairs to put an extra term on the end of the number representing the other sequence there. Now, there are many better ways of representing finite sets, but I've taken the one that's the shortest to write down here. Every sequence could be thought of as representing a set, but of course a sequence puts things in order, and a set is unordered. So many sequences represent the same finite set. What is your favorite way of Gödel numbering finite sets? There's a better way where you get a one-to-one correspondence between finite sets and integers. What is it? Oh? Take binary notation. Every integer is uniquely representable as a sum of distinct powers of 2. Take the exponents to be the finite set. Every number uniquely represents a finite set. But this is quicker to write down for the purposes of today. And then I adapt the idea of Kleene star operation. Kleene thought in terms of an alphabet, and then the language generated by the alphabet. The language is nothing or more than all words in the alphabet, all sequences in the alphabet. So, in a very abbreviated way, given the set X, these are the set of Gödel numbers of sequences, all of the terms of the sequence which are chosen from X. So that's X star here. Okay with those Gödel numbering? So a very basic amount of Gödel numbering of finite data structures here. Of course, you get more elaborate data structures. You can get trees by having sequences of sequences of sequences and so on. So these things can be used in many different ways. Any question? Now, the enumeration operator model, this developed very slowly. It has a very odd history, as I said in the other lectures. Gordon Plotkin, when he was still a postgraduate student in Edinburgh, after I introduced lattice versions of lambda calculus, wrote a report of using sets in ordinary set theory for doing lambda calculus. I didn't understand his model when I first saw the report, but later on I realized the connection to the Lambda Calculus models and wrote Data Types as Lattices paper in the mid-70s there. Gordon, we were invited to Corrado Berm's celebration in Rome, and so I published the unpublished article I had for Strachey on typed Lambda Calculus, and Gordon published his unpublished report on the set theoretical definition of application and lots of other commentary in the Corrado Berm Festschrift. But the idea is really, really simple, and I'll tell you about enumeration operators in a minute. A set of integers and a set of integers, infinite data structures here, we can apply one to the other. Start enumerating x. As you enumerate x, you enumerate all the finite sequences from x. So whenever you see a Gödel number that matches an ordered pair in F, you say F is a lookup table. I just looked up an F that says N produces M. F tells me a number of input-output relationships here. So whenever I recognize from X a validated input, I can then use F to make an output that way. So as you're enumerating F and as you're enumerating X, you're enumerating F of X. And everything is the same type, sets of integers, and F of X is always well defined. This is a total combinatory algebra under this definition. Now, since the evaluation of an application here is done by finite sets, you can just turn this definition around backwards for lambda abstraction. If you have an association of sets from sets, you then say, let's just see which finite sets produce output. And so you go through all the finite sets, and whenever you get output from a finite set, you put it in the lookup table for input, output, that way. And I throw in 0 for purpose, I'll tell you in a minute. So you may not see why this is a good thing to do, but the definition is pretty easy. Any question about it? Okay. Let's see what my next slide is going to be. Sometimes I'm surprised when I go to my slides. Okay, this is the explanation of why it's a model there. And it's based on the fact that the power set of the integers is a topological space. There are two topologies on the power set of the integers that are popular. The usual one is to think of the power set of the integers as a function space 2 to the n. All 0, 1 valued functions on the integers. That's usually topologized as a compact Hausdorff space, and it's homeomorphic to Cantor's set. The Cantor set numerically could be thought of as all ternary numbers to the base 3, where you use only the digits 0 and 2. That's the counter set. That leaves out the middle thirds if you take only digits 0 and 2. And it's in a one-to-one correspondence with infinite sequences of 2 objects. And the topology on the line is the same as the product topology of a discrete space to an infinite power. And that's a compact Hausdorff space. This is, so to speak, only half of the topology. When you do 2 to the n, you record both when things are in and out. You have both positive and negative information about the set. Here, in setting up the neighborhoods, you use only positive information about the set. So the nth neighborhood is the collection of all those sets which share a given finite subset. This says I'm thinking of a finite subset contained in X here, and so I'm only giving in this neighborhood what's in the set, not what's out of the set. It's still a nice topological space. It isn't a Hausdorff space. It has a weaker thing, which in the jargon of point set topology is called a T0 space. The T0 space, Hausdorff spaces are such that distinct points have disjoint neighborhoods. T0 space means two points sharing the same neighborhoods are identical. So that's weaker than saying distinct points have disjoint neighborhoods. And of course, 2 points, 2 sets which share all the finite subsets are identical because every set is the limit of its finite subsets in topology. And now the key thing for the modeling is that you have a notion of continuity on functions of arbitrary many variables, and it works out very nicely. I've written it in a formal way there, but intuitively the definition of continuity is the following. A function is continuous if and only if a finite amount of information about the function value is already determined by a finite amount of information about the arguments. And that's a general kind of topological idea. It's a direct generalization of epsilon delta definition of continuity in the calculus. So we're not using, in this lambda calculus, arbitrary functions. We couldn't use arbitrary functions because the model is already a large size of the continuum. Power set of n has cardinality of the continuum. And the cardinality of arbitrary functions from power set of n to power set of n is 2 to the continuum. Cantor's theorem that you always expand cardinality here. However, if you restrict attention to continuous functions, there are only a continuum number of continuous functions. It's the same thing on the real line. A continuous function from reals to reals is uniquely determined by its action on the rationals. The rationals are countable in number, and so the totality of continuous functions is of the power of the continuum, not of the power 2 to continuum. So that's part of the secret, that we're restricting functions to being continuous. And now for manufacturing continuous functions, it's very easy to see application is continuous because a finite amount of information about f of x is determined by a finite amount of information about x and a finite amount of information about f. Of course, this is just information about one element of f of x, but a finite number of these elements of f of x requires only a finite amount from x and f. So things are immediately continuous. Am I okay so far? So I have an algebra here of sets of integers with a binary operation called application, and everything is using continuous functions. But if I take an arbitrary continuous function, because a continuous function is uniquely determined by what it does to finite subsets, I can make a lookup table on one of the variables there. And if you look back at the definition here, a finite amount of information about lambda x, f of x, will be determined using only finite amounts of information about the additional variables in the things there. I mean, we see the finite amount of information there, but if I'm trying to find a finite amount of lambda, I only need finite amount of information about any of the variables that occur in the expression. So therefore, if you start with a continuous function and lambda abstract on one of the variables, it's continuous in all the other variables as well. So we keep at this level of continuous functions, and now the secret comes out that lambda x phi of x is just the largest lookup table that replicates phi. Okay, and so that's basically the proof that beta conversion is true. It's the largest lookup table that replicates phi. And you check that. And so in terms of this definition, you get, therefore, that if you take a lookup table, it can be a very economical lookup table, and you think of it as determining a function here. This can be very sparse here, but there's a much larger lookup table that gives you the same function there. So I should have written it the other way there, but never mind. If you start with an arbitrary lookup table and apply lambda x f of x, you don't get identically the same thing. Largest lookup table that does the same as f. How am I doing? Is it okay so far? So that's basically why we have a model here, and some. This model could have been discovered in the mid-50s. Several times a week in the middle of the night, I kick myself in bed for not having thought of it when I was a graduate student, because both Myhill and Shepherdson in their paper on effective operations on partial functions, and Rogers teaching recursive function theory at MIT, came up basically with enumeration operators. Myhill and Shepherdson defined lambda abstraction in their paper without thinking that there's an algebra of operators. And Friedberg and Rogers, Friedberg was an undergraduate student of his who solved the post problem. They defined application, but neither group realized they had Lambda Calculus staring them in the face. And if only I had thought of that, oh damn. Here are a few properties of Lambda Calculus. This is what I like to call extensionality, and let's read it here in the special case of equals. Two lambda abstracts are equal in this model if and only if the corresponding functions are pointwise equal. So that's just like saying two sets are equal if they have the same elements. That's the extensionality axiom, and it's even broadened here, involving inclusion there. So many people call eta extensionality, the eta rule, does imply extensionality, but it's an extra thing that says everything is uniquely a function. And so you can find, you can filter out lattices. The power set of the integers is a lattice, and this model gives a retraction of the whole space, power set of n, onto the function space. In other words, the whole space is retracted onto the function space here, and that has a lot of lattice theoretic properties contained in my data types as lattices. We don't have to dwell on that, but here's a nice lattice theoretic property that the lookup table for pointwise intersection of two functions is the pointwise intersection of the lookup tables. And similarly for union, in other words, this retraction preserves lattice properties from the lattice of subsets there. So that's just a glimpse of some of the properties you get out of this when you have the lattice structure of integers to work with. And from the point of view of computability, the computable operators of many variables there are just those such that if you take the total lookup table on all the variables, that's a recursively enumerable set. Friedberg and Rogers pretty much restricted attention just to computable operators, but of course the definition of application can be done with any two f and x in the things. Any questions? Please interrupt me anytime. Now, Turing came to Princeton to do his PhD, and Church had him work on Lambda Calculus. Turing, of course, had introduced Turing machines. What happened was Kleene was given the project of developing arithmetic in Lambda Calculus, which he did brilliantly. And before Turing ever came to Princeton, earlier Gödel was in Princeton and talked about the incompleteness theorems and the principles of arithmetization of syntax and how that's used for his incompleteness results. So Rosser and Kleene took very detailed notes on Gödel's lectures, and they completely understood the method of arithmetization from Gödel's lectures. And then Church realized that from Gödel's approach there, he could get the unsolvability of the decision problem for predicate calculus, because it was clear that in formal arithmetic, it only takes a finite number of axioms to get you sufficiently many properties about one non-recursive set. And so if you have only finitely many axioms to work with, you have the incompleteness of predicate calculus as coming from Gödel's argument. And I always say Gödel would have proved that if anyone had asked him about it, because it's pretty obvious from Gödel's work. But Gödel felt uncomfortable in Princeton and went back to Vienna. He was in a sanitarium for some time, and then he had to escape the Nazis before the war started. But he had lectured in Princeton, and they absorbed all of that, but he was gone from Princeton, so Turing never met Gödel. Kleene and Rosser had finished their PhDs and had to get postdocs or jobs. It was the Depression. You had to go out and get a job to raise your family. So they weren't in Princeton either. So Turing never met Gödel, Kleene, and Rosser, the three people who would have understood his work the best at the time. Now, Turing introduced, as soon as Turing got to Princeton and was apprised of what happened there, he gave the proof. So did I say the right thing? Kleene earlier proved lambda definability in the style of Church is equivalent to Erbron-Gödel computability. Gödel made very heavy use of primitive recursive functions, but it was clear that there are more computable functions than there are primitive recursive functions. And so the question is, what is the extent of computable functions beyond recursion? And so in correspondence with Erbron, they developed the idea of equational computations from recursion equations as defining Erbron-Gödel recursion. But once Kleene could do formal arithmetic completely in lambda calculus, and because he knew Gödel's arithmetization methods, he could prove that Erbron-Gödel computability is as lambda definability, because lambda definability through Gödel numbering can replicate deductions. And so he had already proved computability theory. Is equivalent to Turing machine. Again, just by, in a Turing machine, using Gödel numbers to replicate equational deduction. Now, one of the things that do recursion in the lambda calculus by a fixed point operator, but later on Haskell Curry gave a simpler kind of fixed point operator in terms of his paradoxical combinators. And what it means is self-application allows you to do replication, and replication is at the basis of recursion. You start something and then you call it itself. You have to replicate its program itself to do other computations. So very starkly here, replication does recursion. Start with any continuous function. Lambda abstract on the function being applied to a self-application. Let's call that nabla. Now you can see immediately nabla of nabla. You have to substitute nabla into the definition of nabla, and then that's equal to phi. Nabla of nabla is equal to phi of nabla of nabla. So that's totally cheap way of getting a fixed point for every continuous function. Now I just, from the original lattice theoretic models of lambda calculus, David Park gave very quickly, after I introduced those in '69, a proof that in the lattice theoretic model I introduced, the Curry combinator gives you the least fixed point of a continuous function. But I was able simply to adapt David Park's argument there because the Gödel number I applied to finite structures, the pairs and the sequences, all of that is well-founded. Whenever you take a sequence number, it's much larger than the numbers you put into the sequence. So if you tear a finite structure apart, you always get smaller numbers. That well-foundedness property gives you the fact that Curry's crazy combinator is not only a fixed point, but it is in fact the least fixed point of the continuous functions. Moreover, if you have a computable phi, the least fixed point is also computable. And now we can turn this around for other kinds of computing by taking ordinary things like successor, predecessor, and test for zero, and promoting those operations from single integers to sets of integers. And then we get, using Curry's insights and just using the usual way of thinking from primitive recursive functions to recursively enumerable sets. If we Gödel number expressions by using Curry's combinators and what I like to call the arithmetic combinators here over the power set of integers, you begin with basic Gödel numbers for just the single operators here, and then you continue on by applying one to the other in all possible ways, forever. And that listing, which can be defined recursively, is the same as the universal Turing machine. It is a computable function, and every recursively enumerable set appears as one of the V of V. And you can use that in lectures I gave on recursive function theory. I could use that definition. I find it much easier to program in functional programming languages than to program in Turing machines. So I can do a lot of theorems about recursively enumerable sets with this lambda calculus model and the insight that computability here can be Gödel numbered there. Now, let's go back to the lattice as the steps to taking types. We've already seen two different lattices here, the power set of the integers and the function space of continuous functions. from the power set to the power set. Those are two non-isomorphic lattices. But there are lots of other lattices that are retracts of those, and one very nice retraction operation is in terms of closure operations. Closure operations are very familiar from algebra and from logic. A closure operation in group theory says, find the least subgroup containing a given set of elements from the group, or find the least ring containing a finite set of elements. In other words, you take a, not finite, but any set of elements and close it under all the algebraic operations. More familiar maybe to you is logical closure. Take a set of axioms and close the set of axioms under the rules of deduction. And you go from the set of axioms to what you can deduce from the set of axioms. And of course, if you deduce something from the set of axioms, several different nice lemmas, and then you deduce something from the lemmas that's still deducible. That's a closure operator. And the continuous closure operators were already introduced by Tarski very early on. Deducibility there. The continuous closure operators, just as in a deduction is finite, and so when you're closing under deduction, you only need a finite number of those axioms, and that's continuity of deductive closure there. So the continuous closure operators give you retracts of the power set of the integers to something called algebraic lattices. In general algebra, those were introduced to say what is the lattice of subgroups of a group like, what is the lattice of subrings of rings like, and those are called algebraic lattices because the first best examples came from general algebra. But it turns out that the continuous closure operators, they give you all countably based algebraic lattices as retracts of the power. And these retracts form a Cartesian closed category because in the Lambda calculus you can say, I'm thinking of the mapping of the fixed point to C to the fixed point to D. When you take the closure operator, then the retract is the range of the closure operator. The range of the closure operator is the same as the set of fixed points of it. So a mapping from the fixed points of C to the fixed points of D is a function such that when you restrict attention to the inputs from the fixed points of C, what you get out of it is already restricted to being a fixed point of D there. So incredibly simple algebraic equation here in lambda calculus indicates which of our enumeration operators are mappings between the two retracts, and in fact the whole idea of being a mapping between the two retracts can be expressed as a lambda expression which is equal to the closure operator. So the closure operator is a category, and the structure of the category, products which I haven't written down there, can all be expressed easily in lambda calculus. So Scott's original models can all be found from the closure operators that way. And when you go down to more general types, how much more time do I have? Can you give me 10 more minutes? Okay, a little slow today. What we're going to do is to think of the topological space power set of n, and we're going to take subspace topology, and now we're going to interact with any theoretical quotient of a subspace. Good quotients retain a lot of topology. Odd quotients will give you odd things.